Hi, everyone, and welcome to Virtual Planetarium from the Museum of Science in Boston. My name is Emily. My pronouns are she and her, and I will be your moderator during this program. So that means that if you are watching us in Zoom, you can actually put your questions and comments into the Q&A box on your screen, and I will relay those questions to our main educators. We're also offering live captions during this program. So if you would like to see captions or subtitles, you can click on the CC button on your screen and then select Show Subtitles. So with that, let's welcome our main educators and we'll get started.
Thanks, Emily. Hi, everybody. My name is Katie. My pronouns are she and her, and today I will be your guide as we explore the solar system, but I will not be doing it alone.
Hello, everybody. My name is Talia. I use she, her pronouns, and I will be providing the visuals today.
Awesome. Thanks, Talia. So this month we are going to be talking all about the planets in our solar system. So we're kind of going back to all of the first things that people tend to learn about in school is our own solar system. And everyone loves the planets. Everyone usually learns mnemonics when they're younger about the planets. So there are 4 Tuesdays in October. So each Tuesday we will be covering 2 planets. So today we will be talking primarily about Mercury and Jupiter. So we've split it up. So each week you'll get a rocky planet and a gas planet to get a little bit of the best of both worlds. So right now, what we're looking at is a program called NASA's EYES. It's a free and open source program. You can download it online. You can use it on the web too, I believe, but it's really wonderful because it simulates the solar system and kind of our local area in our galaxy. And it also has options for showing NASA spacecraft that are either in the past, in the present, or even some in the future as well. So you can kind of move time around and see what's upcoming if you'd like, or what has happened in the past. And so this has a lot of cool capabilities and it's free, which is the best part of all. So right now we're looking at a model of our solar system. Our sun is at the center of our solar system, right in the middle there. And then there are 8 planets orbiting around the sun. So if you want, you can say them with me at home, but we've got Mercury, Venus, Earth, and Mars. And then in the outer solar system, we have Jupiter, Saturn, Uranus, and Neptune. So we've got the 4 inner rocky planets and the 4 outer gas giants. I know a lot of you are probably maybe bitterly thinking of a different number rather than 8 planets. You might be thinking of 9. Pluto used to be a planet, but it was reclassified back in 2006 because we just learned more about the solar system. And it turns out Pluto fits a lot better with a different group of objects than it does with our planets. So this is our solar system. It's like our little neighborhood inside of our galaxy. There's only one star and it's the sun, and it's the most gravitationally dominant object in our solar system. Everything is orbiting around the sun. Other stars that you see at night in the sky, when you look up at those constellations, those are all different solar systems. So they're not in ours, but all of them are in the Milky Way galaxy. So hopefully that gives you a better idea of our place in our galaxy or in the universe, even in our solar system. So now let's go ahead and take a closer look at the closest planet to the sun, which is Mercury. Now, surprisingly, first off, you'll notice it looks a lot like our moon. So a lot of the times and I still do it, when I see pictures of Mercury, I'm like, oh yeah, that's the moon. And then I have to take a second glance and I'm like, oh wait, no, that's a planet. That is not our moon. But it has a lot of similarities. It is very heavily cratered. You can see lots of pockmarks all over its surface, including like debris from the impact. So in this case here, we can see that one crater there with material kind of stretching out in all different directions. Those are called crater rays from impacts. And the reason that Mercury has so many craters on its surface is because there's nothing really there to protect it. Mercury does not have an atmosphere. Mercury is extremely small, which means it doesn't have a super strong gravitational pull, which makes it hard to retain an atmosphere. And it's also, since it's so close to the sun, it's about 40 million miles away from the sun, which is close, even though it sounds really far. But being so close to the sun means it gets blasted with the solar wind. And the solar wind is basically just radiation and charged particles that are shot out into space. And so they're hurtling through our solar system. And so that all of the solar radiation kind of strips away any atmosphere that Mercury might have at some point. So it's a combination of it being very small and very close to the sun that it does not have an atmosphere, which means there's not a whole lot to protect it from collisions in space. When we have something entering our own atmosphere here on Earth, you could think of like meteors, they generally burn up before they even hit the ground because there's so much friction in the atmosphere that these objects vaporize in the atmosphere. So because Mercury doesn't have that, there's a lot of impact evidence on its surface. And a fun fact about Mercury's craters is that they are all named after folks from history who have contributed somehow to the world of the arts. So artists, musicians, composers, let's see, what else? Architects, I believe. Did I miss any, Talia?
Authors, lots of authors, lots of musicians, anybody who has contributed creatively to the dancers. There are dancers on there as well.
That's super cool. I love that. I don't know any of the specific names except for Seuss crater. Talia taught me that earlier. There is a Dr. Seuss crater, which is pretty cool.
Seuss, I know there's a Warhol for Andy Warhol. Of course, there is a Tolkien, which is near and dear to my heart, for the professor, J.R.R. Tolkien.
That's awesome. Yeah, the naming schemes for a lot of the surface features of planets and moons are just the coolest. We could do a whole show just on all the different categories and themes for all of them. Okay, so Mercury, it is the smallest planet. We already went over that. It has a weak gravitational pull, but it is moving the fastest, and that's because it's the closest to the sun. So 1 year on Mercury takes about 88 days to complete, or 88 Earth days, I should say, is equal to 1 Mercury year. But it rotates very slowly. I believe it takes about 59 Earth days for it to spin around one time. So its day and its year are actually not that different. Only about like 20 Earth days is really the difference there. It also has the most elliptical orbit of the planets in the solar system. So when we see the solar system from far away, we notice that most of the orbits are fairly circular. They're not perfect, but they're close. Mercury is definitely the most egg-shaped of all of them, or the most oval shaped. So it's got that elliptical orbit, and it is also tilted just a little bit because all the planets, they tend to line up pretty nicely, except Mercury. Mercury kind of sticks out just a little bit more than the rest of the planets. It's tilted about 5 degrees. So a combination between the oval shape as well as this tilt, as well as Mercury's really long day, makes sunrises and sunsets really weird. They kind of bob up and down over the horizon, depending on where you are on Mercury. So because Mercury is so close to the sun, you might think that it would be the hottest planet in the solar system, which is actually not the case. So if we think back to Mercury and it not having an atmosphere, that means that it can't trap in any heat. So the daytime side of Mercury, or the side that's facing the sun, gets really, really, really hot. Not as hot as Venus, though, because Venus has a very thick atmosphere. So the surface of Venus actually gets hotter. But that side of Mercury that's facing the sun is hundreds of degrees Fahrenheit, whereas, and Celsius for that matter, whereas the side facing away from the sun can actually get incredibly cold because atmospheres act like blankets. So an atmosphere will keep a planet nice and toasty. It'll keep it warm, even if there's no sunlight hitting it directly, for a little while, it's still going to be warm. Like on Earth, when we are facing away from the sun, when it's nighttime, it doesn't get really, really cold. And that's because our atmosphere is really good at moving and trapping the heat around our planet. So because there's nothing to trap it in, the other side just gets extremely, extremely cold. And there are some craters that are so deep that the bottoms of these craters have never seen sunlight ever in like 4.5 billion years since the beginning of the solar system. And it's thought that there is a lot of water ice at the bottom of these craters, which is kind of unexpected. You wouldn't really expect ice to be on the planet that is closest to the sun. And one other final fact before we leave Mercury is that it is shrinking. So Mercury is slowly cooling. So over the past 4.5 billion years, it has been cooling since formation and since the chaos of the early solar system. And this cooling is causing it to contract a little bit and get kind of squished and a little like almost like shrivel up, except it's not that dramatic because Mercury has only shrunk, I believe it's like 7 miles over the past 4.5 billion years. So it's an incredibly slow process, but it is kind of a fun fact to say that Mercury is shrinking. All right. Have there been any questions about Mercury or the solar system before we head out to Jupiter?
I have not seen any come in yet. That doesn't mean that they'll come in later. Oh, okay. Hold on. Let me read. Okay, so no, still no questions. Why don't we move on to Jupiter? Because I think we're all excited to hear about it. And then I'll ask questions about Mercury later if we have any.
Sounds great. Yeah, we'll check back in at the end. All right, now we are headed to Jupiter, the 5th planet from the sun. We said Mercury is about 40 million miles away from the sun. Jupiter is closer to 500 million miles away from the sun. So it's quite a hike out there. And it's in the outer solar system. So if you were going to travel from Mercury out to Jupiter, you'd have to pass by the orbits of Venus, Earth, Mars, through the asteroid belt, and out on to Jupiter. So we talked about the smallest planet in our solar system, and now we have arrived at the largest planet in the solar system. If you could open it up like a cookie jar, you could fit over 1,300 Earths inside of it. So it's pretty huge in terms of size. It's also very massive. So these two terms, size and mass, they sound similar, but they are two different things. So size is a measurement of how much space something takes up. So Jupiter's really, really big. It's taken up a lot of space, 1,300 Earths worth of space, but it's also incredibly massive, which is a measurement of how much stuff something is made of. Now, Jupiter is not, it doesn't have a solid surface. It's made up of a whole bunch of gas. So you could never land on Jupiter, sadly, but it has an incredibly interesting atmosphere, which is basically the whole planet, just layers and layers and layers of atmosphere. And something that is probably the most obvious when we look at Jupiter are those bands across its surface. So there's some blues and oranges and whites and grays, and those bands are actually due to how fast Jupiter rotates and the fact that it's made of gas. So one day on Earth takes about 24 hours. Mercury's day takes like 59 Earth days, and Jupiter's day only takes 10 hours. So it's spinning really, really quickly. And we already talked about its size and its mass. It's huge and massive. So all of that material is getting dragged along as Jupiter spins quickly, which means that different gases that have different densities, they tend to separate and form these bands of different gases, which appear as different colors. Now, Jupiter is primarily made of hydrogen and helium, but there are other gases in there as well. Gases like methane and ammonia and a whole bunch of others that are escaping my mind right now. So something else that I think is really cool from Jupiter's quick rotation is that there are tons of storms in its upper atmosphere. So anywhere that you see a circle or an oval shape, that is a storm. And of course, the most popular of all of the storms on Jupiter is its Great Red Spot. So you can see just how much bigger it is than the other storms, except they're all huge. So you could fit 2 to 3 Earths right across the Great Red Spot if you were to compare it to Earth's diameter. And so even some of those smaller storms there, they're not small. They're still the size of the Earth. But the Great Red Spot has been observed for hundreds of years. So Talia's going to fly us right into this spot. So you can make some predictions at home. Think about what you're going to see. What type of storm is it going to be like? And we'll dive in and we'll get out fast so that, we're not hanging around in a really bad storm for too long. So there's lightning. I don't know if folks were expecting lightning, but that is similar to Earth storms. And now we're kind of like in an eye of the storm, and we're passing right out the other side. So if you're thinking the storm is similar to a hurricane, you would be correct. It is. It's a lot similar to Earth's hurricanes. It's just that Earth's hurricanes might last a few weeks before they weaken or they make landfall, whereas this one has been raging for at least 400 years. And really, we only know that because those were the first observations were made 400 years ago. So it could have been there much longer than that. It is getting smaller over time. So in, another few hundred years, we might not see a Great Red Spot on Jupiter anymore. But with Jupiter's track record, with all of its storms on its surface, who knows, maybe there will be another one popping up soon. Now, one of my favorite things about Jupiter is not actually the planet itself. It's all of its little neighbors orbiting around it. So because Jupiter is so massive, it has a very strong gravitational pull. And so it's got a ton of moons. It's got 79 moons orbiting around it. Mercury didn't have any. So Mercury, very small, not a big gravitational pull, but Jupiter is the opposite extreme of that. And so these are all of the moons. You can see just how far out into space Jupiter's gravity extends. You can barely see Jupiter at this point, but all of these moons that are kind of toward the outer orbits here, they are considered captured moons. So moons that were floating by Jupiter that maybe got kicked out, or objects, I should say, not moons, objects that got kicked out of maybe the asteroid belt, since the asteroid belt's really close by, some gravitational interactions that threw one out, and then maybe it was passing by Jupiter and Jupiter's gravity snatched it up and it got stuck in orbit around Jupiter. So these are called captured, and they have really wonky orbits because of this, because they kind of come in at all different angles. But the moons that are closer in to Jupiter have more concentric, nice and neat orbits. They kind of almost look like a little mini solar system. And those moons formed probably when Jupiter formed. So just extra material that was orbiting around the baby Jupiter kind of clumped together and coalesced to form these moons. Now, 4 of them in particular are my favorite moons around Jupiter, and probably some of my favorite moons in the whole solar system. This is an animation of these 4 moons in particular. They are called the Galilean moons. And that's because Galileo saw them through his telescope. He discovered them back in, I believe it was 1610. It was definitely the 1600s. So it was a long time ago, but you're actually able to see these 4 moons through a telescope if you're observing Jupiter. And right there, actually, you could see that there was a little tiny eclipse, a shadow of one of those moons across Jupiter's surface. So these are called, we've got Io, we have Europa, Callisto, and Ganymede. Ganymede is the largest moon in the solar system. It's actually bigger than the planet Mercury. So it is the 9th largest object in general in the solar system, including the sun. After Ganymede comes Mercury. So it's bigger than a planet, but Jupiter is so massive that, it's easily got stuck in orbit around Jupiter. And Ganymede just looks really cool. It's a very old moon. You can see there's lots of interesting features all over its surface. There's a good chance that there is a liquid water ocean underneath the surface. So even though we're really far away from the sun, all the way out here, and it's very cold, underneath the surface of a lot of these moons, it's actually a lot warmer because of something called tidal heating. And I do want to talk more about that, but I'm going to wait till we get to Europa. So that's Ganymede, the largest moon orbiting around the largest planet in our solar system. Next up, we have Callisto, which is considered one of the oldest moons, or at least its surface is one of the oldest, because it has remained relatively unchanged throughout its past. There's really not a ton of geologic activity happening that is changing the surface. So it is thought to be very old, very pockmarked and cratered. Now, this moon is nearly the exact same size as Mercury in diameter. So if you take the measurement from one end to the other, it's nearly the exact same size as Mercury, but it is a third of Mercury's mass. So this object is not it's actually the least dense object, a solid body object in the whole solar system. So it's kind of like a fluffy moon, or a porous moon, I guess you could say. And it's also thought that there may be an ocean under this one as well. But if we're going to talk about oceans under the surface of moons, we've got to travel over to Europa, which is probably like top 3 moons for me in the solar system. This moon is the smoothest one. Its surface is incredibly smooth of any solid object in the solar system, but you can see there are cracks in the surface. And so Europa does indeed confirmed have a liquid water ocean under its surface. Now, the reason that it can be a lot hotter under the surface of these moons is because of gravitational forces from Jupiter. So this tidal heating, as these moons orbit around Jupiter, they're not in perfectly circular orbits, just like the planets. They're in elliptical orbits or oval shapes. And so sometimes at one end of the orbit, the moon is closer to Jupiter. And so the gravitational force is stronger at that end. And then it moves on to the other end of its orbit where the gravitational force isn't as strong at the other end. And so basically it's just getting pushed and pulled as it orbits around the planet, that the insides are like expanding and contracting, and this generates a lot of heat. And so that's why under the surface of these icy moons, conditions are ripe for liquid water. Now, these oceans are probably much saltier than the ones that we're used to, but it's possible they could be breeding grounds for life as we know it. Extreme forms of life that use chemicals instead of sunlight for energy, just because they're so far from the sun and underground. So if we're going to send spacecraft to, outer solar system objects, my vote is for these outer icy moons, and you probably heard all about them last week. Talia talked, I believe, about the Europa Clipper. So more to come on that. And then the last moon, the last of the Galilean moons, is Io, which I love this moon too. It looks like a moldy cookie. You can see from this this angle here, it's got a weird color and there's all these spots on its surface. And that's because Io is the most volcanically active place in the solar system. Nearly everywhere on its surface, there is a volcano spewing out sulfuric acid and all kinds of stinky chemicals into the area around Io. And as a matter of fact, a lot of these volcanoes are feeding the rings of Jupiter. I know we don't really think about Jupiter having rings, but it does. It's just that they're not very reflective like Saturn's are. But they're made mostly of like dust and rock, not very good at reflecting sunlight. But a lot of that material is being fed by Io's volcanoes. So the material that's coming out is getting stuck in orbit around Jupiter and forming a ring, which is pretty cool. So yeah, there we have it. Jupiter and its wonderful Galilean moons. So I will pause and take questions.
Thank you, Katie. I love that you just called Io a moldy cookie. I've never heard that before, but you're absolutely right. Someone is asking, are mass and density the same thing? Because you definitely used both of them when you were talking about Jupiter and even some of the moons.
Yeah, that's a great question. So they are not the same thing, but they are, they can be related. So density is how much mass is in a certain space. That's how dense an object is. So if you take, like a ball of dough and you kind of stretch it out, right? It's taking up a lot of space, but it's the same amount of stuff as it is if you were to kind of crunch it into a ball. So in that case, the mass is the same. It's just that its density is different because the amount of space something is taking up is different. So mass is the amount of stuff something has. Density is that mass in a certain space, certain volume.
Cool, thank you. And I think I see just one more question that we can cover today. Is there a reason why Mercury doesn't rotate as quickly as Earth does, for example?
Yeah, so Mercury is in what's called a resonance with the other planets. So basically the gravitational interactions between the inner planets as well as the sun affect how quickly it spins and also how quickly it orbits, I believe. And is Mercury tidally locked, Talia? Do you know?
It is not tidally locked.
It's not.
Because it is rotating. It's just rotating very slowly. For it to be tidally locked, which basically means, for those of you at home, tidally locked is like what our moon is, where it rotates at the same rate that it orbits, which means we always see the same face of the moon. If Mercury were tidally locked, one side of it would always be facing the sun and the other side would always be facing away from the sun. So Mercury's close. It's not quite tidally locked.
That makes sense, because then its day would be the same as its year, but we already covered that that's not the case.
All right, cool. Well, thank you so much, Katie. Like I said, I think we're officially out of time. So why don't both you and Talia say your goodbyes to everyone?
Bye, everyone. Thanks for joining.
Yeah, definitely. Thank you all so much for joining us today. Let me share my PowerPoint with you all. Here we go. I did add the website that Talia was using, the NASA EYES website, so that some of you could check it out if you were interested. It's definitely a really fun tool to experiment with. If you would like to see any of our other virtual offerings, you can visit mos.org/MOS@home. And then if you're interested in supporting the museum, you can visit gauge.mos.org/welcome. So with that, I hope you all enjoy the rest of your week, and we'll see you next Tuesday.